Welcome students. Today we shall learn some more formula and derive them. These integrals will basically have a certain way to derive them. You must note how we derive and what are kind of technique that we use to derive them, because that will help you when you are finding some more difficult integral for which you may not know the formula. So, the technique in itself will be very useful while finding integrals. So, we shall look for the integrals which will contain the algebraic expressions or the polynomials. As a first example, I will take the integral of a particular form dx by x square plus a square. So, this looks very similar to one of the integral which we have seen dx over x square plus 1. So, first I will show you what technique we can use in order to derive this integral. So, what we do is that if we substitute x equals to a tan t, then this will give us dx is equals to a sec square t, and then the unknown integral I becomes a sec square t dt by x square plus a square. So, since x is a tan t, therefore, x square plus a square equals to a square tan square t plus a square, though a square can be taken as common, and this will give you tan square t plus 1. You know 1 plus tan square theta is sec square theta, therefore, we can use that trigonometrical identity. This will give you a square sec square t. So, we get here a squared sec square t and dx is a sec square t. So, ultimately the two terms will get cancelled here, sec square t and sec square t, a will get cancelled with a, and this you can write as outside the integral because it is a scalar, therefore, this can be written as integral of dt. So, you see it has been converted into a very simple form. So, I can write it as 1 by a integral of dt is t plus a constant of integration, which could have been written as c by a and then again a new constant c1. So, I am directly writing it as a constant c, and t I already know is that from the relationship of a x and t is that x is equals to a tan t, therefore, t will be x by a tan inverse x by a. So, this I will get 1 by a and t equals to tan inverse x by a plus c. This we have to always keep in mind that original integral is with respect to x, and therefore, final answer should be a function of x. So, ultimately when we reach to t by a, we have to replace this t into the substitution which we made here. Ultimately, the formula which becomes is that it is important formula to note now, dx upon x square plus a square equals to 1 by a tan inverse x by a and plus of course, the constant of integration. Next, we consider another example of integral dx over x square plus a square square the root. So, now we are going to integrate dx over square the root of x square plus a square. Again, as I told you the way we have used in the previous case. This was dx over x square plus a square. So, can we use the same technique? Let us see what will happen if I substitute here x is equals to a tan t. So, this will again similarly we will get dx is equals to a sec square t dt. So, that finally, we will require t is equals to tan inverse x by a, or we will see that for whether we need that relationship at a later stage and how shall we need that relationship at a later stage. So, the integral now turns out to be dx is a sec square t dt. This will become, in the previous problem we have evaluated that x square plus a square is same as a square sec square t. Therefore, this will become square root of a square sec square t, which will be same as a sec t, and therefore, finally, we shall get sec t dt. So, we can use the formula directly. So, we already know integration of sec t dt is same as log of mod of sec t plus tan t modulus plus constant. So, using this formula here, we will find that this is log of sec t plus tan t plus the constant. Now, we have to again go back from t to x, and if I substitute this t is equals to tan inverse x by a, here I shall get x by a, but here I will get a complicated relationship sec of tan inverse x by a. So, what I should do is that I should not substitute this t directly, rather I should use another trigonometric relationship with sec and tan, which is, we know that sec square t can be written as 1 plus tan square t, and therefore, sec t can be written as square root of 1 plus tan square t. So, instead of sec t I will replace that. So, this I will get log of square root of 1 plus tan square t plus tan t plus constant, and finally, now you can easily see from here is that the relationship will become tan t. So, t is equal to tan inverse x by a will become tan of tan inverse x by a, inverse function operator. So, we will get x by a here, and here tan inverse tan of tan inverse x by a squared. So, that will give you x by a squared, square root of 1 plus x square over a square plus x by a plus constant, which after further simplification I can write here as this a square plus x square plus x whole divided by a, and you know log of m by n goes to log m minus log n. Therefore, that log a constant that can be written separately. So, this finally expression in terms of a on x's only will be looking like log of x plus square root of x square plus a squared minus log of mod a plus c. So, finally, this calculation leads to log of mod x plus square root of x square plus a squared, and this log a is anyway constant. So, adding with it another constant and renaming this with constant C 1, you know the constant C 1 does not matter what you call this. So, ultimately this constant C, since it is arbitrary, we will keep it with the same name as constant C. So, this turns out to be dx over x square plus a square the root becomes this formula. Now, we will look for another kind of integral which are of this form, integral of dx upon x square minus a square. So, we wish to evaluate how to find out the integral of this kind, difference of two squares which goes to so, the first step which we can take here is that immediately is that what if we write it in that product form. So, now what benefit we have got here is that writing this is linear term and this linear term, and if somehow we are able to write them in terms of linear term alone, then we can utilize the logarithmic formula. Can we do that? So, let us try to do this. So, what I will do is that I will write this integrand separately. So, our integrand is 1 by x minus a into x plus a. What I will do is that if I look at the term carefully, so numerator is a constant, and if I take the difference of these two terms, that is x plus a minus x minus a, I see that I ultimately get 2a. So, what I do is that I divide and multiply it by 2a. So, that it is written as 2a over x minus a multiplied by x plus a. Well, as I told you that this is 2a is nothing but the difference between these two terms, and therefore, I can write it as x plus a minus x minus a So, if you look at it carefully further, you can see that this can be broken into two parts, 1 by 2a, x plus a over x plus a into x minus a. This will give you 1 over x minus a minus 1 over x plus a. So, if you look at the term which we started with was 1 over x minus a into x plus a, it is converted into two terms, both of which having denominator as a linear factor, and for the linear case we have logarithmic formula. So, therefore, if I write this integral dx, because the integrand has been factorized in this way, so this 1 over x minus a will be replaced as 1 over 2a integration of 1 over x minus a minus 1 over x plus a dx, and this you simplify a bit and then first use the distributive property here for the integral. So, it will give you dx over x minus a, then minus 1 over 2a dx over x plus a, and then you integrate it. Well, 1 by 2a can be carried forward together. So, 1 by 2a, this will become logarithmic of mod of x minus a minus 1 by 2a logarithmic of mod of x plus a, and then the constant of integration as c. You know 1 by 2a can be taken as common, as then again log of m minus log of n will be same as log of m by n. So, we can write it as 1 by 2a log of mod x minus a over x plus a and plus constant of integration c. The integral I is evaluated in this form, and the trick which we used here is a denominator which was a quadratic form which could have been factorized. We converted into two factors, both of which are having a denominator which is a linear function. So, we will apply the same trick and we will look for another formula. What if we have to evaluate dx over a square minus x squared. So, now with the previous example, we can see that we can write it as 1 by 2a. Again here the term which is in the numerator is constant. So, the difference should not be taken such a way such that the variable term comes there, and therefore, we must write it as a minus x plus a plus x divided by a minus x into a plus x, which are the factors of this quadratic term dx. I can write it as 1 by 2a, and a minus x divided by a minus x into a plus x will give you integral of dx over a plus x, plus another integral will give you dx over a minus x. So, that you will get 1 by 2a. This will give you logarithmic of mod of a plus x. So far there is no problem, but here if you see this term is negative minus of x. So, we have to evaluate it separately, and if I use the idea of substitution here again, or if I use the formula, you can see that this will become log of modulus of a minus x divided by minus 1, which is the derivative of this term, and plus a constant of integration. So, you can check yourself that what will be the integral of a minus x. So, ultimately what we got here is that this negative sign will make this sign negative, is 1 by 2a log of mod of a plus x minus log of mod of a minus x, and plus a constant of integration, which will give you 1 by 2a log of a plus x over a minus x plus constant of integration. So, integral for a square minus x square comes out to be of this form. Let us take example, how shall we apply this formula. So, choose this example in this following manner. Suppose that we want to evaluate this integral. So, if you notice here, we should make a choice, or we should make a substitution in such a way so that it should be converted into a form which we already know, is that I can write this integral as thrice of x squared dx over x cube squared plus 2 squared. And further, if I notice, then the derivative of x cube, this is a factor in the integrand, turns out to be 3x squared dx, that is another factor in the integrand. So, that becomes a good choice for us, and therefore, we will put x cube to be an variable t. So, that trace of x square dx equals to dt, and this calculation leads to dt over t square plus 2 squared, which leads to the formula which we developed first, dx over x square plus a square. It will be 1 by a. So, 1 by 2 tan inverse x by a. So, here it is t, therefore, formula is modified accordingly, t by 2 plus constant of integration. Now, original problem was in x. So, we must convert it back into x, and therefore, it should go to 1 by 2, that is 1 by a, t is equals to x cube. So, it gives me tan inverse x cube by 2 plus constant of integration. So, knowing the formula helped us in evaluating this integral. So, whenever we are writing, we must mention that which formula we are writing. For example, here we are using the formula. So, while evaluating, we should mention that, as we know, dx by x square plus a square is 1 by a multiplied by tan inverse x by a plus constant. Now, if I take another example, simple and quick example, is to integrate x square over 1 minus x raised to power 6. Then again you can easily see here that I can write it in the similar fashion as I did in the previous example, is that I can write it as x square over 1 minus x cube squared. So, the suitable choice becomes x cube equals to t, which will take you to thrice of x square dx over dx equals to dt, which will take you x square dx to dt by 3, making the substitutions here 1 over 1 minus t squared dt by 3. This leads to 1 by 3 constant comes outside, integration of dt over 1 minus t square. You know the formula of dx over a square minus x square. So, this goes to log of a plus x over a minus x plus constant. So, this will lead to 1 by 3 log of, here a is 1, x is t. So, I have to modify the formula accordingly, 1 plus t over 1 minus t plus constant of integration, and then finally, I have to convert into x, 1 by 3 log of 1 plus x cube over 1 minus x cube plus constant. So, the integral I comes out to be this much. So, oh sorry, I missed this 1 by 2a here. So, this will make, in this case, since a is 1, so it will make 1 by 3 into 2, that will make it 1 by 6. So, now we shall further look at some more formula of similar kind. One of them is another important formula. So, to find out the integral of the kind, I is equals to integration dx over square root of a square minus x square. You have already seen a similar expression for formula dx over 1 minus x square, which was for sin inverse x. So, you should expect something similar here. If you look at this expression carefully again, what substitution can be made. So, the idea which we are going to use here is that we are going to substitute x is equals to a sin t. Why that x is equals to a sin t? Because in that case I will get here the expression as 1 minus sin square t, which will take you to the cos square t, and then square root will help us in evaluating those terms. So, let us make the substitution. This will give you dx is equals to a, sin t will give you cos t dt. So, the integral I turns out to be a cos t dt divided by square root of a square minus x square will become a square into minus a square sin square t. So, I will take a square as common, it will become 1 minus sin square t, and you know 1 minus sin square t is cos square t, taking the square root. So, this term will become a cos t. So, the same as the numerator a cos t. So, ultimately I will get here only dt, which will lead me to integral t plus c. X by a plus constant. The integral comes out to be equals to, and that should be expected because it is a similar formula to 1 minus x square. So, as I did for the case of a square plus x square, if you want you can take a square as common and then convert x by a into t, and then again you write, and then you will figure out that you will get the same formula. Further we shall look for another example, dx over square root of x square minus a square. This is different than previous case, x square minus a square. So, in this case the substitution which we made earlier will not work, we have to figure out some other substitution. Notice the relationship of sec and tan. So, we can see that if I put x is equals to a sec t, then this should help us, because then it will become a square sec square t minus a square. So, sec square t minus 1 will appear there, which can be converted into tan. So, this should help us. So, let us look at what expression I should get from here. X square minus a square is equals to a square sec square t minus a squared a square sec square t minus 1, and this relationship I know already, it is tan square t, therefore, this is a square tan square t. And since a is equals to a sec t, so this will also give us dx equals to a, differentiation of sec t is sec t tan t, and then dt. So, making the substitution there, let us see how this integral evolves. So, this becomes a, replacing dx by a sec t tan t dt divided by square root of x square minus a square. X square minus a square is a square tan square t, this will become a tan t. So, this tan t and a are cancelled, and ultimately I am left with sec t dt. This formula we already know, integration of sec t dt is logarithmic of sec t plus tan t. So, this we will use logarithmic of sec t plus tan t. Again, as earlier, we can see from here is that sec t is known to us. Sec t can be easily evaluated from this relationship, since x is equals to a sec t, therefore, sec t is equals to x by a. What about tan t? Fortunately, we have a relationship of sec t and tan t. So, we know that 1 plus we have the relationship tan t is equal to square root of sec square t minus 1, which will help us get this tan t to be square root of x square by a square minus 1. Substituting the value here, we get logarithmic of sec t is x by a plus tan t is square root of x by a square minus 1. plus constant. After a bit of simplification and taking this log a as along with this constant c, I can write this as log of mod x plus square root of x square minus a squared, then minus log a plus c. So, I will call this as a new constant c itself, since c is arbitrary. So, it will take care of that. So, integration of dx over square root of x square minus a square turns out to be. So, we will take up now to certain specific integrals. Let us look at the integral of the form dx over ax square plus bx plus c. So, we have to find out what will be the integral of this kind of function. You can easily see that this is not of the form of either x square plus a square or x square minus a square, which we have, or a square minus x square, which I have shown earlier. But if we use little algebra, this can be converted to one of those forms. So, check the denominator function ax square plus bx plus c. What we can do here is that we can write it in this form. So, our first attempt will be to make this x terms as a perfect square. So, this is the quadratic term, this is the linear term, there should be some constant term which should make it as a perfect square. So, if you look at it carefully, what you can do is that x square, so the formulation should be x square plus 2 some number multiplied by x plus square of that number. So, this b by a x, I can write it as 2 b by 2 a x. This will help me understand that what should be the next number to get the perfect square. So, this x square 2 b by 2 a x. So, this is same as b by a. So, I have written this number here same. So, this means that if I have b square by 4 a square here, it will become a perfect square, but that is not there, this is c by a. So, I have to add this b square by 4 a square, I have to subtract that b square by 4 a squared, and then I have to write this c by a. So, what I have done here is that I have added and subtracted this number, so that this number becomes a perfect square. Look at it, x square twice of x into b by 2a plus b by 2a whole squared. That means that it is x plus b by 2a whole square. So, this entire term. This term I will write it as with a plus sign, c by a minus b square over 4 a square. We really do not know what is the sign of this expression. This will be dependent on what is the value of a, b and c. So, depending on the values of a, b and c, this will be either a plus sign or a minus sign. So, in general, I can write this number x plus b by 2a as some new number capital X, and c by a minus b square upon 4 a square as some number, let us say k squared, and since I do not know the sign what will appear. So, I will put both the signs. So, if it is coming as a positive sign, I will keep it as a positive sign. If it is coming as a negative, I will keep that sign as a negative sign. So, ultimately the integral I, you can easily see that is small x plus b by 2 a is equal to capital X. This will make dx to be a d of capital X. So, d of small x is same as d of capital X, and therefore, the expression I will be converted into d of capital X upon x squared, 1 by a will be outside, because this is the denominator expression. This is the denominator expression which is written in this form. This is a capital X square plus minus k square. So, this will be 1 by a capital X square plus minus k squared. Now, look at it carefully. This expression is one of the form dx over x square plus a square or dx over x square minus a square. So, one of the formula can be useful. Sometimes if sign of a is negative, then the similar formula can also lead you to the form of a square minus x square. So, you can also use that relationship a square minus x square. We will see it with the help of an example and see how it develops. So, let us choose one example for you. Let us find out the integral of nine x square plus 6 x plus 5. So, this is the same expression as I told you earlier, a x square plus b x plus c, a is positive. So, let me write this 9 x square plus 6 x plus 5 separately, taking 9 as common. I should put both the. So, both of them here. So, taking 9 as common, you can write it as x square plus 6 by 9 of x plus 5 by 9. So, you can easily see that what you need to do here is that this basically is x square plus 2 by 3 of x plus 5 by 9. Further, you can write it as perfect square. So, x square, this is 2 times 1 by 3 of x. So, 2 times 1 by 3 of x, therefore, you should write it as 1 by 9 plus and minus of 1 by 9 and then plus of 5 by 9. So, the entire calculation should lead you to 9 x plus 1 by 3 whole squared, and then 5 by 9 minus 1 by 9 will take you to 4 by 9. So, this is plus sign now, 4 by 9, I will write it as 2 by 3 whole square. So, the integral I now can be written as dx over 9 is taken as common, x plus 1 by 3 whole square plus 2 by 3 whole squared. So, we shall get 1 by 9 and replace this x plus 3 by some number capital X. So, that x plus 1 by 3 is equals to capital X. So, that dx is equals to dx. So, we will get d of x over x square plus 2 by 3 whole square. So, ultimately I will get 1 by 9. This is x square plus a square, x square plus a square integral I already know now, it is 1 by a. So, I will put here 1 by 2 by 3 tan inverse x by a. So, x by 2 by 3 and plus constant integration. So, after some calculation I can see that the number turns out to be 1 by 6, this 3 gets cancelled here, 3 to the 6, tan inverse 3 by 2 of capital X, but capital X is small x of 1 plus. So, So, it is x plus 1 by 3 plus constant of integration, and finally, if we want to further simplify it, I can write it as 1 by 6 tan inverse, introduce this 3 by 2 inside. So, this will give me 3 x plus 1 by 2. So, this will make me 3 by 2 x plus 1 by 2. So, that 3 x plus 1 by 2 plus constant of integration. So, now I will show the same example which I took again. That instead of going the way we had gone, we could have taken a different path, because ultimately the idea should be taken from here is that we have to make this as a perfect square somehow. So, what I can do here, but I must warn you that initially you should go and you should solve the problem the way we have derived them. Later on you can use these ideas. So, 9 x square plus 6 x plus 5, I can easily see that this is nothing but 3 x square. So, 3 x squared, and this is second term is nothing but twice of 3 x. So, I can easily make it as a perfect square by just adding 1 here. So, since 5 is already there, so I can break it into 1 plus 4. So, that this entire term will make me as 3 x plus 1 whole square plus 4. So, immediately I can write this integral I as dx over 3 x plus 1 whole square plus 4, and make a substitution that 3 x plus 1 is equals to t. So, that 3 dx is equals to dt. So, that this integral transforms into dt by 3. I can take this 1 by 3 outside. This makes as t square plus 2 squared, which will further lead to 1 by 3. This formula already we know now is 1 by a tan inverse t by 2 plus constant, and t is known to us now. So, this is nothing but 1 by 6 tan inverse 3 x plus 1 by 2 plus c. So, which is the same result as we observed earlier. Further, I will show you the example of another kind with a similar idea, that can we solve the problem of the form dx over square root of ax square plus bx plus c. Again the idea is same, we should be able to write this ax square plus bx plus c into either of the form of x square plus minus some k square, as, or if a is negative, then it can be written as k square minus x square. So, depending on the form of this expression, this term can be converted into one of these forms, just as was the previous case. So, I will show you with the help of an example. Suppose that we choose the example as dx over square root of x square plus 2 x plus 2. So, this as I can see easily from here, it is x square plus 2 x. So, if I add 1 here, this will make a perfect square, and therefore, I can write it as dx over square root of x plus 1 whole square plus 1. Replacing x plus 1 by a new variable t, you can find out that dx is nothing but dt. So, that this integral converts into dt over square root of t square plus 1, and this formula we know that dx over square root of x square plus a square is actually a logarithmic function x. So, dx over x square plus a square, this formula we have already evaluated, it is logarithmic of mod x plus square root of x square plus a square and plus constant. So, here the variable of integration is t, therefore, it is t plus square root of t square plus 1 mod plus constant of integration, and this t is nothing but x plus 1. So, therefore, this will give you square root of x plus 1 plus square root of x plus 1 whole square plus 1 x plus 1 whole square plus 1 plus c, which you can further, if you want to, you can write it as x square plus 2 x plus 2. So, plus constant. So, you can see that with the use of this formula, it has become very easy to evaluate this integral. These examples have further applications when we have integrand which is of the form p x plus q divided by a x square plus b x plus c, or p x plus q divided by square root of a x square plus b x plus c. So, we shall look for these two forms. So, suppose that we have to evaluate the integral of the form p x plus q over a x square plus b x plus c, or we have to evaluate it of the form p x plus q over square root of a x square plus b x plus c. So, the procedure for both of for the evaluation of both of these integrals is similar, only fact that the formulas which will be used, they will be little different, because here there is a square root. So, those square root formulas will be used, and here it is a square. So, those perfect square formulas will be used. So, let us choose one of them. Let us choose this first example here. So, to solve this expression, let me call it as I 1 and let me call it as I 2. To solve I 1, what we do is that we write numerator p x plus q as some constant times the derivative of the expression of the denominator, that is a x square plus b x plus c and plus another constant b, where these are some unknown constant which will be determined later. Notice carefully, the numerator is a linear term, denominator is a quadratic term. Therefore, if you differentiate this quadratic term, you will get a linear term. So, these two expressions are comparable. So, linear expression, this expression will also give you a linear expression and another constant. In this case also p x plus q equals to, this is another quadratic. So, we will take this quadratic term a x square plus b x plus c, the differentiation of this a x square plus b x plus c. So, let us look at what will happen. So, p x plus q will become a, differentiation of this term will give you twice of a x plus b plus b, and ultimately if I compare, since these are the polynomials on both the sides. So, they are comparable. So, I must get p, the coefficient of x here, same as the coefficient of x here, is twice of small a times capital A, and q, which is the constant term here, must be same as capital A times b plus b. in order to satisfy this relationship, this expression must be satisfied. So, if you look at the equations now, you have two equations in two variables. We do not know what A is, we do not know what B is, but we got two equations and therefore, we can simply solve them. So, from first equation you can easily solve A is equals to P by 2 A, and then you substitute that A here and you can solve B. So, ultimately from these equations you can know what your A is, can know what your B is, and once you know that what your A and B's are, you substitute them back here and then replace this P x plus q in this expression by this expression and break this integral using the linearity property into two parts. So, the first part will have so I can write the integral I1 here, this integral I1, this will be broken into these two parts. The first part will have capital A integration d by dx of ax square plus bx plus c by ax square plus bx plus c dx. So, this will be because this px plus q is inside, a is constant taken outside, plus b integral 1 over ax square plus bx plus c. So, I already know these expression now. Now, if you notice carefully, this denominator term has this numerator term as derivative. Therefore, if I take this as new variable t, this will come to as log this integral will come as a logarithmic function. This again I will convert into a perfect square and get the integral. So, this integral I1 can be evaluated. We will see this with help of an example that how this can be evaluated, and in fact similar procedure will be used for the case, but in that case what will happen is that the derivative will appear here and there will be denominator will be having a square root, and therefore, in that case you will get 1 by root t, and that also you can evaluate. So, that will not be a problem. So, I will show you it with help of an example. 6x minus 2 divided by 3x square plus 2x minus 1 dx. So, you can see easily this is of the form px plus q divided by ax square plus bx plus c. So, let us use the idea which we developed now. 6x minus 2 should be written as capital A unknown terms d by dx of the denominator, 3x square plus 2x plus 1 plus b. So, that you know the differentiation of this will give you 6x plus 2 a times 6x plus 2 plus b here. So, 6x minus 2 equals to a times 6x plus b. This will give you very easily, you can compare the two terms here. This is 6 ax is equal to 6, therefore, a must be equals to 1, and this is twice of a plus b is equals to minus 2. So, since a is 1, so this will become b is equals to minus 4, twice of a plus b is equals to 2, therefore, b is equals to minus 4, right. So, substituting these values in the integrand, what I will get is that I, which is this expression, equals to a, which is 1, times, let me write it first, d by dx of 3x square plus 2x plus 1 all divided by 3x square plus 2x plus 1 dx. Later on you can directly write this term as 6x plus 2 divided by b. So, b is minus 4 integral of 1 over 3x square plus 2x minus 1, sorry here minus 1, this is also minus 1, sorry. So, this term after evaluation you can see that if I choose this number as t, what I will get here is that integral of dt by t minus 4 times this term here 3 x square plus 2 x plus 1, again using the same formula as we have done earlier. Here let us take first of all choose 1 by 3 outside. So, this integral can be represented as dx divided by x square plus 2 by 3 of x minus 1. This you can easily see x square plus 2 by 3 of x minus 1 can be written as x plus 1 by 3 whole square minus 4 by 9. You can now write it, and therefore, this integral first will give you logarithmic of t, logarithm t plus a constant, let me call it as C1, minus 4 by 3. The other integral will give you dx over x plus 1 by 3 whole square minus 2 by 3 whole square. So, this formula also you know, and you can simply evaluate the final integral. T is the expression which is 3 x square plus 2 x plus 1. So, this will be logarithmic mod of 3 x square plus 2 x minus 1 minus 4 by 3. This is dx over x square minus a square. So, it will come 1 by 2 a, 2 times 2 by 3 log of x minus a. So, x plus 1 by 3 minus 2 by 3 over x plus a. So, x plus 1 by 3 plus 2 by 3, and then the constant C1 was already there. So, we will put it as C1 plus C2, which I will write finally as a new constant C. So, finally, you will get 3 x square plus 2 x plus 1 minus 1, 2 x minus 1 minus this 4 cancels and this 3 cancels, logarithmic of 1 by 3 minus 2 by 3 will give you again minus of 1 by 3, 1 by 3 and 2 by 3 will give you 1. So, this will get you 3 x minus 1 over 3 x plus 3 x plus 3 plus a new constant C. One can further do some computation or simplification to get this expression here. So, this is finally we saw that how we can simply solve this example, and we can get the answer by using that technique. And in the similar fashion, we can also take up the example where the square root of this term is given. So, we can use that. So, with this we summarize what we learned today is that we learned some more integral of some more functions which involves rational functions of algebraic expressions. We shall in the next class we shall learn some more new techniques for evaluating these integrals. Thank you.